Welcome to a screencast on the Bohr model of the hydrogen atom. You're probably aware that when light shines through a prism, the prism splits the light into its spectrum. And if we look at or observe the emission spectra of various light sources, like for example a fluorescent light or an incandescent light, what we end up seeing in those cases is what's known as a continuous spectrum. We get all the colors of the rainbow, and they blur from one into the next. But if we look at the emission spectra of specific gases and look at that through a prism, what we end up seeing is something that's known as a discrete spectrum. We get very specific or discrete lines of very specific colors, and not all the colors of the rainbow, and the lines don't blur into each other. Okay, what's going on here? Well, we're going to look specifically at the hydrogen spectrum and what is going on to make this discrete hydrogen spectrum. Here's the visible hydrogen spectrum. It has 4 visible lines, a red, a blue-green, and 2 purple lines. If we look in the infrared and ultraviolet as well, there are other lines that can't be seen with the naked eye. And the hydrogen spectrum was explained by a guy named Niels Bohr in 1913. And his theory is as follows. He envisioned an atom the hydrogen atom, as a nucleus surrounded by electron orbits. So here's an electron in the first orbit or first shell. And he postulated that the electrons could only have certain specific quantized energy levels or energy values. And that's because the electrons could only be in certain quantized, very specific orbits. The electron could be in the first energy level, or the first electron shell, if you prefer to call it that, or the first orbit. And he envisioned the electron as actually circling the nucleus as if it was, say, a planet circling the sun. That's not really what's going on, but for now we're going to go with this as his model. The electron could be in a second energy level, or a second electron shell, or a second orbit, or a third, or a fourth, and so on. Now, if energy, and again this is Bohr's postulate or theory, if energy was absorbed by the atom, then the electron, which normally likes to be in the first energy level, if the electron absorbs energy from that photon, it goes to a higher energy level. So here the electron went from level 1 to level 2. The electron's now at a higher energy level, and the energy of the photon has been used up to do this. Now the electron, it turns out, isn't stable in the second energy level, and it will tend to return back to the first energy level. When it does that, it gives off some energy. And when the electron goes to the lower energy level and gives off energy, it gives off energy as a photon of light of very specific energy, or a very specific color or wavelength, if you prefer. Now, of course, the electron could absorb a different amount of energy, and in this case, it's a photon of a different amount of energy than in the first case, and go to a different energy level than previously. So here the electron absorbed energy and went from the first to the third level rather than the first to the second. Again, the electron's unstable in this higher energy orbit, and once it has made this transition to, in this case, a different energy level, it will give off a photon of light and go back to a lower energy level. And the photon of light is, again, very specific in energy or wavelength or color, but it's different than the previous one. So different energy photons given off. Now, for most elements, analyzing what's going on with these energy levels is really complicated. It's too complicated to do analytically. But for hydrogen only has 1 electron, and it's actually simple enough for us to do. And right now we're dealing with Bohr's model of explaining what's going on. One thing to note, Bohr's model hinges on the notion that a given quantized energy level can be explained by treating the electron as a wave, and that wave has only an integer number of wavelengths in an electron orbit. So here is an example of an electron orbit with 1, 2, 3, 4, 5, 6 wavelengths corresponding to that orbit. A different orbit could have 3 or 4 or 1 or 5, but it has to be an integer number. And if you do the math on this, if you kind of do what Bohr did to describe what's happening, you can visualize the hydrogen atom as having the proton as its nucleus. First energy level we're going to call n equals 1. Second energy level we'll call n equals 2. Third energy level n equals 3, and so on. And the energy levels increase in energy as they are farther from the nucleus. Now it gets cumbersome to draw these sort of circular energy level pictures, these orbit pictures, and so what we often do is make a translation where we use a line to represent the energy level, and so the lowest energy level for hydrogen, n equals 1, is represented by a line that's low on the page. The next highest energy level, n equals 2, is represented higher up by a line. Third energy level, higher yet, and so on. And here is kind of a streamlined version of this. Energy increases going upward. Lowest energy level is n equals 1. Next energy level is n equals 2. It's higher than n equals 1. N equals 3 is higher yet. 4, 5, 6 increasingly higher energies, and we eventually get to the infinity energy level. And it turns out that the energy of a given level has a very simple mathematical relationship. It's given by E sub n equals negative k over n squared, where k is a specific constant for hydrogen, 2.18 times 10 to the minus 18th joules. N is an integer, 1, 2, 3, 4, etc., on up through infinity. And E sub n is the energy of a particular level, of the nth level. And n is specifically called the principal quantum number, and you can also think of it as the specific energy level or orbit we're dealing with. Worth noting, this is the energy level diagram specifically for hydrogen. This equation works specifically for hydrogen. Other elements are much more complicated than this, but have similar conceptual basis. And then also note, this is not quite to scale. The gap in energy from n equals 1 to n equals 2 is actually even bigger than it appears here. And then from n equals 2 to n equals 3, that's a smaller energy gap or energy difference. N equals 3 to 4 is less than 2 to 3, and so on. So those differences in energy become smaller and smaller as we go higher in energy, but they're actually even more dramatic than is shown here. Okay, so let's do a little bit of calculating with Bohr's theory and with the energy relationship here. Let's calculate the energy of level 1. Well, it's pretty simple. K is 2.18 times 10 to the minus 18th joules. There's a negative in front of it, and then we divide by the energy level, which is 1 squared. And the math on that is really easy. Dividing by 1 squared is the same value. So the energy of level 1 in the hydrogen atom is negative 2.18 times 10 to the minus 18th joules. Same idea for energy level 2. E sub 2 is negative this constant divided by 2 squared, or divided by 4. That works out to be negative 5.45 times 10 to the minus 19th joules. E sub 3 is that value divided by 3 squared, or 9. That works out to be negative 2.42 times 10 to the minus 19th joules. And we could keep going for energy level 4, 5 on up. And again, let's clean this up a bit. So there's E sub 1 through 3. And quick note, E sub infinity turns out to be 0. So if we divide a number by infinity, or in this case infinity squared, dividing by a really huge number gives us 0. And so Notice all of the other energies are negative, and the E sub infinity is actually our zero of energy, and that's just the standard that is used in describing and doing the math with the hydrogen atom. Okay, now a little bit more. If we look at our energy level diagram and look at our orbit picture here, if we have an electron in this case, the second energy level, and it goes down to the first energy level, it gives off a photon of light when it does this transition from level 2 to level 1, and that photon happens to be too high in energy for us to see. If we now look at an electron being in energy level 3 and going to level 2, so there's the orbit picture for the level 3 to 2 transition. Here's the energy level diagram picture for the transition from level 3 to 2. That happens to be a photon of red light that we can see. And for hydrogen, the 4 to 2 transition, the 5 to 2 transition, and in fact the 6 to 2 transition, which I'm not showing here, all of those produce visible light of aqua or blue-green, purple, and purple respectively for the 4 to 2, 5 to 2, and 6 to 2 transitions. And let's do a calculation with this particular hydrogen atom. We'll specify the third to second energy level transition, and we'd like to figure out the energy, frequency, Greek letter nu for frequency, and wavelength, Greek letter lambda for wavelength, of a photon produced from the transition from the third to the second energy level. And let's do it. So the E photon, the energy of the photon, comes from the 3 to 2 transition. I'm going to write this as delta E sub 3 arrow 2 because we're starting at the third energy level and we're going to the second energy level, and we're looking at the change in energy for that. Well, delta E is E final minus E initial, so E2 minus E1 is final because we end up in 2, minus initial because we start in 3. We just figured out E sub 2 was negative 5.45 times 10 to the minus 19th joules using that formula E sub n equals negative k over n squared. We also just figured out that E sub 3 is negative 2.42 times 10 to the minus 19th joules. And if we then subtract E sub 3 from E sub 2, we get negative 3.03 times 10 to the minus 19th joules. The negative means energy is given off when this transition occurs. And so we then note that energy is given off. It's given off in the form of a photon, so a photon is emitted. And then the photon has an energy of 3.03 times 10 to the minus 19th joules. No negative sign because the negative simply means energy was given off. Okay, so now we've determined the energy of the photon. How do we figure out the other things? Well, we know that the energy of a photon is related to the frequency of a photon by E equals h nu, where h is Planck's constant. So solving for nu, we get nu equals E over h. We just figured out that the energy of the photon is 3.03 times 10 to the minus 19th joules. Planck's constant is 6.626 times 10 to the minus 34th joule seconds. Note that units of joules cancel. Doing the math, dividing this out, we get 4.57 times 10 to the 14th. And then notice the units are per second, which is also called hertz. So the frequency of the photon produced by this transition is 4.57 times 10 to the 14th hertz. And then last but not least, we want to find the wavelength. We know that wavelength is related to frequency by the speed of light. So lambda times nu equals c. Solving for lambda, which is c over nu, we then plug in the speed of light, 2.998 times 10 to the 8th meters per second. We divide by the frequency of 4.57 times 10 to the 14th per second, which we just calculated. Per second cancels. Do the math, and we get 6.56 times 10 to the minus 7th meters. And We often, sort of by convention, convert this to nanometers. So you might want to make sure that you can do this conversion. And converting meters to nanometers, 6.56 times 10 to the minus 7th meters is 656 nanometers. And that is the wavelength of the light produced, or photon produced, by the 3 to 2 transition in a hydrogen atom. If we relate this to the observed spectrum of hydrogen, that is actually the red line that we see in the visible spectrum. And then the 484 nanometer blue-green line and the 434 and 410 nanometer purple lines correspond to the 4 to 2, 5 to 2, and 6 to 2 transitions, respectively. And then, of course, all transitions, not just visible ones, are possible, so we can have electrons also transition from level 2 to 1, or 3 to 1, or 4 to 1, etc. We can do the similar calculations. Those happen to be non-visible light, but same process, same basic idea. And that is it for the Bohr model of the hydrogen atom screencast.